I always like to start each lecture with a brief review of the previous lecture. Last time we talked about why it's important to study hardware, and Charles said that I was a little harsh, but my point is that for anyone who's not a computer engineer, which is pretty much everyone, almost everyone, they would reasonably assume that processors are still getting faster. And they would assume that because processors up until 10 years ago were getting faster, just right along same pace as Moore's law. In other words, they were getting twice as fast with every new generation. And also up until just recently, we didn't have some capabilities that we have now. Like we didn't have 4K video on a phone until a few years ago, and we just recently got things like animojis, and video game graphics get better all the time. So, I think most people would reasonably assume that processors are getting faster when in fact these advancements are because we're designing these special purpose hardware solutions to introduce these new capabilities. So that was my point with that. So yeah, and also it's not, well, at least according to this plot, it's not that processors are not getting fast at all, but they have certainly slowed down quite a bit over the past 10 years. This plot, now the reason for that is, I guess, is a debatable. This plot clearly suggests that the limitation with processor technology, with CPU technology, is power, and that in order to get more speed out of a processor running software, you'd have to be able to give it more power, and you can't because you'd have power management problems. That may be true. Sure, certainly is partially true. I always believed it was because of practical issues related to programming general purpose processors. Doing very fine-grained parallelism is difficult, and at some point you just can't have a processor automatically extract parallelism from code that was written for a general purpose processor. Even multi-core processors will bottleneck at the memory interface, and ILP processors, like your typical single core on an Intel processor, have fundamental limits as to how many instructions they can have in flight in execution at one time, and that's because of unpredictable branch performance. It's limited by branch predictors. So that's I think another big reason why processors aren't getting any faster. So in the future, we're going to have processors like all those ones I showed you on the Snapdragon. The Snapdragon's got all these different variety of application or domain-specific processors on them, and they all have their own specific way to program them that is very different from just what you learned in 145, 146, and 240. They all have specialized programming models. They're hard to program. You have to write code in a way that's explicitly parallel. So that's the issue. But there's all these new innovations going on right now with memory, processor and memory type architectures and array architectures. Like people want to have cameras that each pixel comes in and goes into its own tiny processor, and they all get processed in parallel, and that kind of stuff. Focal array processors. There's a lot of stuff in neurosynaptic processors where you do ASICs that do neural networks. There's work in automata processors. There's all kinds of crazy stuff going on. So it's an exciting time. And I also mentioned last time as well that it looks like even Moore's law may be coming to an end. I mean, it has to eventually. And the strange thing about that was, people always predicted it would end, but this is the first time, starting with the Broadwell and Skylake processors, that Intel has failed to deliver a new fabrication technology. Yes?
What about the i9? Do you know, is that like, they just came out, do you know if it's like?
Yeah, the i9, I think, I don't know a lot about it, but I mean, it's basically a faster processor. It's in this, as far as I know, it's in the same 14 nanometer fabrication technology. It's got some aggressive features on it.
You
But
It's a rebadged Xeon.
yeah, it's like a server processor, sort of. You know, it's has the same problem all these processors have, which is if you look at its single core performance, it's not that much better than older ones, and even multi-core. You know, it runs into these memory bottlenecks. Yes.
What about Ryzen 2 with 7 nanometer coming later this year?
Yeah, well, that's my point, though. It's taken longer than expected to get to 10 and 7 nanometer, and we don't know when that's going to come out. But like I said, eventually, once we get down to half nanometer, it's you know we're smaller than the spacing between the atoms. So unless we switch to a different material that has different spacing, although I think I used to have a slide that showed, gosh, I deleted it, and I remember when I was preparing these slides, I deleted this figure, and I couldn't remember. I deleted it because I couldn't remember where I put it. But I had a figure that showed a gallium arsenide crystal unit cell, and gallium arsenide is another semiconductor material, as is gallium nitride. There's other semiconductors than just silicon. But my point of that figure was that the spacing between the atoms was the same in all of them. So you know, even switching to a new semiconductor material isn't necessarily going to save us. You know, obviously, some people think that quantum computing is going to be the answer. But for the time being, we'll eventually get to the end. And what that's going to mean is that we're going to, like I was explaining last time, we're going to have a fixed budget, a fixed real estate. Now, we could always go to bigger chips, but then you have to worry about yield. Then you have to improve yield. Because the reason why chips are limited to the size that they're limited to is if you go any bigger, your yield goes down. You get less useful chips out of the fab process. So unless we can improve yield and go to bigger chips, and bigger chips, though, will consume more power, so that's not necessarily a solution either. So what's going to end up happening is that microarchitects are going to become more, the job market for microarchitects is going to become bigger because we're going to need people with innovative hardware solutions. Yeah.
What was yield that you have to account for? What's the problem?
Yield is the percentage of dies. When you fabricate a chip, you pattern the design onto a disk, a silicon disk. That's called a wafer. You have a wafer. So you start with ingot, which is a cylinder. You cut the cylinder, the ingot, into disks, very thin disks that are called wafers. And then you cut the wafers into the chips. Now, the reason they do it in a clean room because they try to prevent any from that wafer from being contaminated, but it's unavoidable. You're going to have some defects in the process. And if you have a defect on the wafer, if you have larger dies, larger chips, then that defect will take out a larger percentage of that wafer, meaning that you'll get less useful chips out of the wafer and less chips overall. So it has a big effect on the economics of fabricating semiconductors, going to a larger die. What a lot of companies do now is they'll accept some bad chips, but if you have a GPU or an FPGA that's just a very simple repeated structure, you could then say, well, I'll sell this bad chip instead of as an i7, I'll sell it as an i3 and just turn off 2 of the cores because one of them has a defect on it. You can play games like that. But there are some economics involved, basically. And like I said, if you make bigger chips, you can tell what happens. Like GPUs are bigger than CPUs, and they use more power. Yes?
How much do you think chip space optimization can be improved on or anything to maybe increase the amount of space for work?
The way they are now, you use every usable spot. You pack them in. In fact, Google has this chip called the TPU, the Tensor Processing Unit. It's a neural network chip that Google uses. Like when you talk to the Google Assistant, it actually gets processed by this ASIC that Google came up with. And David Patterson led the team that made it. And he was giving a talk, and he was showing a picture of the TPU, and he says, you'd be amazed. We actually tried to get this. Our goal was to get this chip out as fast as we could, and we actually didn't use all the area on the chip. And the audience gasped, like, oh, like that's unthinkable. But that they were in such a hurry they didn't take the time to fill up every last spot on that chip. But in most cases, that is the case. That's normally the.
I guess what I was saying is Moore's law might be coming to an end, but even then, there's going to be some rule keeping us
Yeah, it's going to be like, what are your trade-offs? Maybe we should have a 4-level cache and make the other levels smaller. Maybe we should sacrifice registers for cores. Maybe we should sacrifice floating point units for data paths. Yeah, it's all the job of a computer architect. So, but just to be clear, the way Moore's law worked was it was a partnership. You had the fab guys that were doing photolithography. They were making these increasingly smaller transistors. And in partnership with them, you had the computer architects that were finding ways to use these new transistors in innovative ways, right? So they were the ones that came up with instruction level parallelism and multi-core designs and multi-level caches. And it was all ways to take advantage of these extra real estate that was given to them by the fab guys. Eventually, though, the fab guys are going to be like, we're done. And then it's going to just be up to the architects. And so I expect that the industry will then start hiring more architects at that point. That was the idea, right? That's why a class like this is relevant. Okay, so moving along here. Chapter 1 talks a lot about abstraction and hierarchy, and these are all important topics, and this is kind of underlies the way that you design digital systems. This figure is this is from the book. I don't completely understand, I don't completely agree with some of the stuff. Like application software isn't necessarily entirely built onto operating systems, because application software does use operating systems when it makes a system call, right? But otherwise it runs directly on top of the architecture, right? So that's kind of an odd choice that they would do it like that. So some of this box should actually be right over top of the architecture. The architecture is, hopefully you learned this in 212, the architecture is the interface between the software and the hardware, and the architecture provides an instruction set that you use to program the chip. It's the native language of the chip. And then the microarchitecture is a set of data paths that implement each one of those instructions. Make sense? So it's like one level down is the add instruction. What is the add instruction? Well, the add instruction requires that you fetch it from memory, decode the registers, feed the register values into the ALU, take what the ALU produces and send it back to the register file. So there's 4 data path and also increment the program counter to get ready for the next instruction and possibly predict if there's a branch and that kind of stuff. That's all part of the microarchitecture, right? So that's the programmer, or if you're writing an assembly language, or the compiler, sees the architecture, and then under the architecture, under the hood, is the microarchitecture. Now, in the case of most processors, this microarchitecture is trade secret. We don't really know exactly how an Intel processor works. Kind of know what it basically does, but not all the details. The microarchitecture is built on these basic library of cells. One of the things the book points out that I like is that if you look at a cell library, cell libraries are pretty simple. They're not that many. There's not that many components that you have to build these larger microarchitectures from, and that's intentional. That's to simplify the design process. The book calls it discipline. But even like, for example, the architecture, ideally it would just have a few instructions that the compiler needs to worry about having to use. Although, some processors have a lot of instructions, but ideally you would have a relatively small number of instructions that you would have to worry about for programming. Does that make sense? Okay. So those are just kind of some concepts. Design hierarchy is something we're gonna look at more closely once I start covering Verilog, which is the hardware description language. Verilog emphasizes this idea that you create a module, and that module instantiates other modules, and then you drill down into those modules and you find other modules, and eventually you get to these leaf nodes, which are the very, very primitive things like logic gates. So there's this design hierarchy. But we'll talk much more about that once we get into HDL. Number systems, this is a review from 211. It seemed like everyone was pretty comfortable with this, right, so far. We're gonna, from this point forward, I'm gonna assume that you're pretty comfortable with binary numbers and hexadecimal numbers. Also, this idea of ranges. This is becoming important in neural networks because companies, everyone's really excited about neural networks and doing machine learning and hardware. And you can fit more neurons into a chip if you reduce the precision. So NVIDIA, for instance, now has this Volta GPU. You might have heard about it. And they had to introduce these new cores, GPU cores, that can process lower precision numbers. And it was designed to speed up machine learning, right? NVIDIA now has a chip that does this too, and of course Google. Google's TPU, I believe, is an 8-bit chip. You might think 8-bit, wasn't it like the original Nintendo 8-bit, like in 1985? What's up with, and Google's latest, their crown jewel of the data center, the TPU, is also 8-bit, like the 1985 Nintendo? Yeah, except it's 8-bit, but it has 64K multipliers on it. It has this huge array of multipliers. And so you can do very high throughput neural calculations on it. Okay, so anyway, when you talk about reduced precision, the first question you have to ask is, well, what's the range of numbers? So with an unsigned number, it's 0 to 2 to the nth power minus 1 is the range. And that is always hard to say because it's 0 to, whatever your value is, 2 to the n minus 1. There you go, right? We're the minus 1. So it's like, if it's an 8-bit number, it's 2 to the 8th power, which is 256. Minus 1 is 255. So 0 to 255, right, is your range. If you have a signed number, then it is negative 2 to the n minus 1, right? So if it's an 8-bit signed number, it's not 0 to 255. It's going to be negative 2 to the 7th power, so negative 128, to 2, and this is where things get weird. It's 2 to the n minus 1 minus 1. That's how 2's complement. This is a 2's complement range, right? So it would be negative 128 to positive 127. So that negative 1 is in both the exponent and down here, it's in the exponent and also not in the exponent, right? You guys with me? Okay. All right. So hex numbers are just shorthand for binary. Of course, we talked about most significant bit and byte, least significant. Prefixes, we talked about addition and 2's complement. So the book has a kind of a neat, this thing. This thing is kind of neat. It shows a number line. This would be for a 4-bit number. So a 4-bit number would go, if it's unsigned, from 0 up to 15, which would be 15 would be 2 to the 4th power, which is 16 minus 1. And then if it's a 2's complement, it would be negative 8 to positive 7. So same number of values, but it's kind of shifted by 8 to the right. Now you might say, well, what is the point of this number line? Well, the point is if you look in this negative part, if you're comparing two numbers, you have to be careful because if it's a negative number, well, actually it works out, right? If it's a negative number, like for example over here is negative 4, 1100. Negative 3 is 1101, right? So that is actually, if you're comparing them, it appears that the negative 3 is a higher number compared to negative 4, but you can't compare it directly to numbers that are positive, right? If you're doing value comparisons, right? Because obviously 6 is a greater number than negative 1, but yet negative 1 is 1111 and 6 is 0110. Does everyone follow that? I'd lose everyone with that. They also show sign magnitude. I didn't talk about that last time because, frankly, I don't think it's relevant. Okay, this is not in the textbook, but I think this is important. Fixed point is how you have a binary number and you want to be able to express fractional values. Now, in your programming classes, like in 145, 146, you probably learn that anytime you need a fractional number, you should be using a floating point number, right? Right? So you got integers and you got floats. The difference is integers are whole numbers and floats are fractional numbers. But you can actually represent, you can use a fixed point, which is where you just have an n-bit number, but you just assume that m of those bits are fractional bits. They're to the right of the decimal. So this is an example of a 6-bit number with 4 fractional bits. You guys, does that make sense? You seen this before? Okay. Yeah, they used to cover this in robotics. I don't know if they still do. But I cover it in 313 actually. Yeah. I should have remembered that. But yeah, anyway, yeah. So the point is, this is neat though, because remember I talked about significance and you have to read numbers from right to left for their significance. Well, in this case, once you hit the decimal point or the radix point, the significance of the value that comes immediately to the right of the decimal point is 2 to the negative 1 if it's binary, right? So this bit carries a significance of 1/2. This one is 2 to the negative 2nd power, which is 1/4. This is 1/8, and this is 1/16. Make sense? So now the crazy thing about fixed point, though, is that if you talk about precision, what is the precision of a fixed point number? You might say, why would you talk about that? Well, because we've got single precision and double precision in the floating point world, right? So everyone talks about precision when it comes to floating point numbers. So what's the precision of a fixed point number? Well, the crazy thing about it is that it depends on the value that you put in there. Because precision is really about significant digits, significant figures, right? And the number of significant figures doesn't include any leading zeros, right? So basically the precision of a fixed point number is the number of bits, but you have to subtract out any of the leading zeros. You guys with me? So precision is essentially the number of unique values you can represent, right? But that depends on it depends on the magnitude, right, of the number. Okay. Also, their accuracy depends on the number of fractional bits. So this number, this 6-4 number, has an accuracy of 2 to the negative 4th power, which is 1/16. That's how close I can get to representing an actual number, right? If it doesn't fall as a 1/16 of a value, then I'm going to have some approximation error. I'm going to have some, I'm going to be rounding off. You guys with me? So the way that you would convert, like for example, if you have a number and you want to convert it, like say I've got a number like let's say I've got, now let's go 2.69, right? And then it's like, okay, I've got a fixed point number that is 3 bits non-fractional, and I've got, 4 bits that are fractional, right? Kind of like that one, except that one I have 2 and 4, right? So 7 total bits, so this would be a 7-4 number, right? So you have to convert this in 2 steps. You have to take the 2 and convert it. So the three positions. So the 2 would be 0, 1, 0, right? And then you have a decimal point, and then it's like, well, what is 0.69? Well, to figure that out, the way you convert it is you say 0.69, and you double it. So it's kind of like the decimal. Remember when you go from decimal to binary, you keep dividing and you keep taking the remainder, right? I showed you that last time. when you go from a fractional decimal number and you want to go to a fractional binary number, you go the opposite way. You double it. So you double this number, and this is going to be 1.38, right? And you take that 1 off, and you put that there, and that's what becomes the first fractional bit. So you also read these numbers from top going down, right? Then you take the 0.38 and you double it, so you get 76, right? 0.76. So you put a 0 there. So that would be the next bit would be a 0, right? And then you take the 76, you double that, and you get 1.52, right? And so there's a 1 there. So there's a 1 there, right? And then you double it again, you get 1.04, and there's a 1 there. But the problem is now I've run out of bits because I only have 4 fractional bits. So I have to stop. So this is the closest now I can get to that 0.69. Well, how close did I get? Well, it's basically, what is that number? That's going to be 11, 8 plus 3, right? 11 over 16, right? Because 16 is 1/16 is that unit in the last place, that least significant bit, right? So that value is 11, it's 11/16. I don't know what that is exactly, but it's close, but not right on the money. We got some error there. Calculator 11/16. Yeah, 6875. So this gets me to 0.6875, which is close, but whatever the difference there is my approximation there. OK, so that's fixed point. All right, switch gear again. Let's talk about logic gates. Logic gates, I'm sure you guys have seen this. You must have seen this in 211 quite a bit. We've got not single input. It complements the input, so y is not a. So we have a little truth table here. If a is 0, y is 1. If a is 1, y is 0. A buffer doesn't do anything. It just takes the input and sends it to the output. So from a Boolean perspective, buffers don't do a whole lot. But from an electrical perspective, they amplify this signal, right? So a buffer will allow whatever produces a buffer will allow it to drive a bigger load, capacitive load, right? So if you've got something that produces a, but you want to fan it out to a whole bunch of other gates, whatever gate produced a might not be strong enough. So you put this buffer in here to strengthen that drive. AND gate is only produces true if the two inputs are true, and OR only produces a false if both inputs are false. And then, of course, we've got XOR. Some people call it XOR, NAND, NOR, and XNOR. NAND is the negated AND, NOR is the negated OR, XNOR is the negated XOR. XOR is sometimes called a parity operation. It's essentially you take the inputs and you add them up and you take the modulo too, So in other words, you're asking if there's an odd number of 1 bits. XORs, of course, form the basis of an adder circuit. It's what you use to build an adder. And then you can have multiple input logic gates. So 3-input NOR, 3-input AND, right? Any questions about that? I'm going through that fast because I'm assuming you guys have seen that. OK, so let's talk about something you probably didn't talk about in 211. In 211, you just assumed everything was 0, 1, or true or false, right? But what is that actually? That doesn't really exist in reality. There is no binary in reality. Binary is in terms of digital logic is a conceptualization of analog circuits. And the idea is that you try to have basically 2 voltage levels in your chip. You have a ground, which is going to represent a 0. So ground or some low voltage represents a false or a 0. And then a true is when you bring it up to the other voltage, which is VDD. I should have looked at it. I always forget what the DD stands for. It used to be called, when I was in school, it was called VCC, and the CC stood for common collector. I forget what the DD, something drain, something. Anyway, VDD is just another name for the power supply. What is the voltage that powers the digital part of your chip? Okay? And so we want to basically try to alternate between ground and whatever this voltage is, right? And that's our 1, 0, right? So there's a lot of switching, a lot of wires that are transitioning between ground and VD in the maximum power supply. Ground and just doing this all the time on there. The problem is that, as you might imagine, nothing's perfect, and sometimes we don't get quite down to ground. We don't get quite up to VDD, and also there's noise that affects everything. I mean, every time you have a wire, it picks up noise because wires are also antennas. So you pick up crosstalk from nearby wires. And the other problem is that when you've got a bunch of gates on a chip and they're all switching between 0 and VDD, it generates noise on the power supply. You get fluctuations in the power supply. In other words, what happens is as you transition from 0 to 1 and 1 to 0, during that transition, you temporarily short out the gate. You temporarily create a low impedance path between the power supply and ground, and it causes the power supply around that gate to dip a bit, and it creates real spiky noise, which is why mixed signal chips, which is where you have one chip with both analog and digital components, which is in everyone's phone right now, because you have to have analog circuits in your phone in order to have a modem, LTE modem. But whenever you have a mixed signal chip, you have to isolate the digital parts of it, because otherwise all that noise created in the digital part will actually affect and degrade the analog part. Anyway, so the idea is that generally speaking, if you look at the output of a gate, it tends to try to pull its output down pretty close to ground for a 0 and pull it pretty close to VDD for a 1, right? But then in between, what do you do with the output of a gate? Well, generally you connect it to you connect it to the inputs of other gates, right? That's what you're doing with it. And noise will affect that wire, which will pull up the voltage of a 0 and it'll pull down the voltage of a 1, right? The good news is that if you look at the inputs for a typical logic gate, they have some tolerance for that. And it has to do with the way that the gate works internally. So let me back up here a second. So ideally, the way this would work is if you look at this plot, the x-axis here represents the voltage of the input, right? And so as you go from 0 to VDD, at the halfway point, like say I have a 5-volt chip, I can set this threshold of 2.5 volts. So I can say anything less than 2.5 volts is a 0, anything more than 2.5 volts is a 1. And what should happen there is if I have a buffer, it's kind of hard to see, there's a buffer here, A comes in, A is the input, Y is the output. So this is an identity function. I'm just trying to say, I'm trying to pass the value of A. Ideally, if the output is the y-axis and the input is the x-axis, as I ramp up the input closer to VDD, it'll keep producing a 0. In other words, this buffer will condition my input for me. It'll say, yeah, I see you're giving me a 0. It's 1 volt, but that's a 0 because that's below the halfway point between 0 and 1. So as I go up in the input, it'll keep the output at 0, and then at some point, once I pass some threshold, it'll immediately jump up to 1, right? So this gate, this buffer, is going to act as kind of is going to clean up my signal, basically, right? It's going to clean it up. If I don't have it exactly at one end or the other, it'll interpret it one way, and then it will regenerate that signal as a clean 0 or 1. But as you might imagine, that's not how real hardware works. This is the way it actually looks closer like this curve, where as I increase my input voltage on this gate, on this buffer, the output will start to creep up slowly. It'll slowly creep up until you reach this point called the unity gain point, where the slope becomes 1, at which point it kind of shoots up pretty fast. And this gate will basically turn into almost like an amplifier, almost like an op amp sort of. And then beyond a certain point, it'll level out again, right? So the goal is to avoid putting it as an input, or avoid any signal in your circuit from being in that forbidden zone, which is between, well, it's marked by the unity gain points here, but in the book they refer to this as VIL and VIH, which stands for the voltage of the input being low and the voltage of the input being high. So they give two different thresholds, right? Once you're below VIL, you're 0. Once you're above VIH, you're 1, right, for the input. Now the output, on the other hand, the output is a little better, because if you even as long as you stay outside that forbidden zone on the input, the output will still look better than the input, right? Because the output will say, as long as you're below this VIL, then the output will be below this VOL, voltage output low, which will be lower than VIL. Does that make sense? You guys with me? So in other words, what I'm trying to say is that basically what this gate is doing is it's cleaning up the input a little bit. The input has a margin. It has a noise margin. The noise margin is basically how much noise you can add to the input of this gate before it'll flip the output, or before it'll become kind of non-determinate. So in other words, you can't go into this forbidden zone. If you go in this forbidden zone, the output of the gate will be unpredictable. But as long as you stay outside that forbidden zone, which is, which depending on your process voltage can be pretty small, although nowadays that's not true so much anymore. I'll get to that in a minute. But you stay outside this forbidden zone, and the gates, the digital logic will clean up. The transistors will clean it up. Yes? That's what I thought. Drain. But what's the other D stand for?
If you have two different drains, one of them is a major drain, and so you call it drain.
Oh, okay.
Or like I heard direct drain.
I don't. Okay. I haven't heard that. That could certainly be the case. Okay. So you've got basically the noise margin is defined as the difference between noise margin high is the difference between the voltage output high and the voltage input high, right? So basically, it's the amount of noise that you can add to the input of a gate and still be able to recover an output, or have it interpret the input as you intended. All right. Okay, but let's talk about that noise margin though for a second. So back in the 1970s and 80s, chips ran at like 5 volts. So 0, ground was 0, 5 volts was 1, true, right? And then as time has gone on, that voltage has dropped quite a bit, especially recently. One of the things that chip makers are doing is they're dropping that voltage. It's now, at this point, I think it's below 1 volt. The power, if you look at VDD on a modern chip, they're bringing that voltage lower and lower because the amount of power you use is proportional to your voltage. So if you bring the voltage down, you use less power. That's the principal reason for that. You guys with me? And there's also another phenomenon called, they don't talk about it in the book, but there's this thing called Dennard scaling, which was back in the, Dennard scaling was something like Moore's law, which said that the amount of power that you would use per unit area of a silicon chip remained constant regardless of how many transistors were on there, which meant that even we're doubling the number of transistors on the chip, the power hasn't changed as long as you keep the same chip size. So for a given chip size or a given chip area, no matter how many transistors you put in that area, the total power will stay the same. That was great, because that way we could keep pushing Moore's law without paying for it in power. But at some point about 10 years ago, might have been a little longer ago, Dennard scaling stopped, and it was because of the transistors were getting so small that the physics were changing, and Dennard scaling is no longer the case. So now chips are eating up more power as you increase the density of the transistors in there, right? So what do you do about that? Well, a bunch of stuff. Use power gating, you turn off parts of the chips you're not using. Frequency scaling, slow the chip down if you don't need it, right? That's become real popular. Clock gating, where you don't turn off the power, but you turn off the clock to parts of the chip you're not using. This has created the dark silicon phenomenon, where it turns out that even on a typical Intel processor, you can't actually use every part of that processor because it would burn up. So in every usage case, there's at all times, there's always guaranteed to be parts of the chip that are shut down. It's called dark silicon. And the other thing is dropping the voltage, just using a lower power supply. The problem that this has caused is that it's made that forbidden zone smaller. And the reason for that is because the actual threshold of the transistor, which is where that unity gain point is the threshold of the transistor, the actual threshold, the internal threshold of the transistor, hasn't changed since transistors were invented. It's been 0.7 volts from now all the way back to the 60s, 50s and 60s. Hasn't changed. So even though we're dropping the supply voltage, we're actually reducing the noise margin by doing that because the transistor thresholds haven't changed at all. It's inherent in silicon and semiconductors. So what's happening is that as they continue to drop this down, so it's kind of this weird thing that's happened. Dennard scaling stopped. We want more performance. Moore's law is still going. Pack more things in there. Power density is increasing out of control. We have to maintain our thermal envelope. So drop the voltage, use dark silicon and drop the voltage, but oh no, now the noise margin is going low, and now we're more susceptible to transient soft errors. So now we have to put in fault tolerance features in the chip. We got to put ECC in the RAM and all this stuff. We end up with more faults. So that's another problem that we're going to have to deal with in the future, is increased incidence of soft errors. Because you don't only have to worry about crosstalk and power supply noise, but even cosmic rays and stuff can cause these soft errors when you're operating so close to your noise margins, which we do because of Dennard scaling. Okay, all right, now let's switch topics one more time. And this is something I know you haven't heard before, unless you heard me give a talk maybe I think I used to talk about this in 190, not for a while though. So let's talk about silicon for a second. So silicon is I think it's the second most common element on the planet. Very, very common element. The problem is that it generally does not occur in nature as pure silicon. In nature, you can go to the beach and you look at sand on a beach, that's all silicon. But it's not silicon, it's silicon dioxide. It's actually glass. It's kind of like very small particles of glass. It's not pure silicon. Pure silicon is not easy to make. You have to grow it. And that's when you make chips, you have to grow pure silicon, and it grows as a crystal. And so what you're really doing when you grow it is, if you look at the periodic table, silicon is in this column labeled 4 on the periodic table. That means it has 4 valence electrons. It's in column 4. It's a group 4 element. Silicon, because it has these four valence electrons, it will form covalent bonds with each silicon atom in a crystal will form covalent bonds with 4 of its neighboring atoms. And it creates this really cool crystal structure that looks like this. Each atom is at a different angle. It's kind of a neat thing. It's not something that you can get off the beach. It's fairly expensive to make this. Now the strange thing is that it's called a semiconductor because it doesn't really conduct electricity. I don't think it conducts electricity a little bit, but basically you wouldn't want to try it. It has a very high resistance. But you can do this thing with silicon that's kind of neat. You can dope it, meaning that you can use this process called ion implantation, which used to be done by a gas, and now it's done by particle beam. But the idea is that you can take an element from group 3, like boron, for instance, I think is what they use, or I think they still use boron. You can take boron and you can shoot it into the silicon lattice. And the boron atoms are able to take the place of some of the silicon atoms in the lattice. But because they only have 3 valence electrons, because boron is a group 3 element, it creates a hole. Now, by itself, that's cool, but the really neat thing about that hole is the hole moves. So in other words, you have the boron atom in there, and what ends up happening is the boron atom can pull in a valence electron from one of its neighbors in the lattice. But if it does that, whoever it pulled it from now has a hole, even though that atom it might have borrowed from might have been a silicon atom, but now it has a hole. It has this weird it's still silicon, but it has a lack of an electron basically inside the lattice. It has a hole, and that hole becomes a charge carrier. And a charge carrier is, well, anything that can carry a charge. So if I took a cable like this and held it up and put like 40,000 volts across it, as I move those cable closer, once I got it close enough, there would be this arc, right? And that arc is where the air in between the 2 electrodes becomes a plasma. And once that happens, the plasma becomes a charge carrier. That's why you can do that. That's why you can arc electricity. Basically turns the air into a charge carrier. Otherwise, air is not a conductor. It's the same thing here. Those holes become charge carriers. So if you dope it more, you get better conductivity because you get more charge carriers in there. Likewise, you can put a group 5 element in there, like arsenic. This is, by the way, why you don't... semiconductor fabrication places are nasty places to go because they got a lot of really nasty chemicals in them. And part of one of them is arsenic, because they got to take arsenic and they got to shoot that in there too. But when they do that, the arsenic takes the place of one of the silicon atoms, and you get an extra electron. And again, that electron has mobility and becomes a charge carrier. And you put more in there, you get more mobility, you get better conductance, right? So that's the neat thing about silicon. That's the whole secret of everything. Everything is kind of built on, all computers are built on that concept. Now you can do stuff like if you use boron, this hole becomes a p-type semiconductor, and if you put an extra electron in there, it becomes an n-type. And the way you remember that is I know what P and N stands for. Taylor doesn't have to look that up. P is positive, N is negative. So positive is where you have a hole as your majority carriers, and N-type silicon is when you have electrons as your majority carriers, right? So if you take a P and an N and you stick them together and you form a junction, it becomes a diode. And a diode will only conduct electricity from P to N, but not the other way around. So you get this diode, but diodes are basically useless in terms of logic. What's really neat is if you create a transistor with it, which is a little bit more complicated than a diode. So the idea with that is, remember I was talking about the wafer before? The wafer, when you get the wafer, when you grow your silicon crystal, you get the wafer. The first thing you do is you pound it, you implant it and make it a p-type. You dope it and make it p-type. Not really, you don't dope it a lot, but a little bit. You make it a p-type. That means the substrate of the chip is p-type silicon. Then you use masking, you use photolithography to block off parts of the chip. And the parts that aren't blocked off, you nail that with the N-type doping, right, which is going to be your arsenic. So whatever is exposed through that mask, you shoot an arsenic beam at it, and you create these things called diffusion areas. So this is a cutaway view. This is like a sandwich that you cut, right? Now the cool thing about this is that this ends up, and then you leave a gap in between them called the channel, right? And this creates a transistor because the substrate forms the bulk terminal, which is the fourth terminal that we often don't even show in circuit schematics. But the two diffusion areas that are little islands, and by the way, just to be clear, if you have P-type silicon and you nail it with an arsenic beam, it'll reverse it. It'll go from P to N. You know, you can go the other way, right? If you have, that's what's happening here. So, but you create these little islands, and that becomes your source and drain, and then in between is your channel, right? And the channel is actually protected by silicon dioxide, which is glass, completely insulator. And then on top of that, you put polysilicon, and that becomes your gate. So the gate, the source, drain, and gate are terminals. And under the gate is the channel, but the channel is not a terminal, but the channel is a very important part of the chip. When I was talking about why is Intel missing the deadline on their 10 nanometer chips, they said, oh, 10 nanometer Coffee Lake, that'll be out in 2016. They're 2 years late. That 7 nanometers refers to the channel length. That's the distance between the source and drain. It's the smallest feature inside of a chip. And that's what the photolithography process is named after. By the way, Intel, for the record, one of the things they had to do to get so small was the channel is actually three-dimensional. This picture is the old style, but nowadays the channel actually comes up and this gate actually forms around it. That way you get the surface area not only on top of the channel, but on the sides of the channel too. They call those Intel calls it the 3D gates or something, 3D process. But basically all it means is that the 7 nanometers or the 10 nanometers or the 14 nanometers, not big enough. This won't work. The only way to make that work is to cheat and make this a three-dimensional structure where you use 3 sides of the damn channel instead of 1 side like is shown in this picture, right? So that's how modern transistors work. Anyway, so you've got this source and drain, and the idea is that in an N-type transistor, if I charge up this gate, it becomes a capacitor because you guys know from circuit, capacitor is, well, first of all, let me back up. The P-type silicon is grounded. So because we ground this P-type silicon, that ensures that we don't have any interference from these diffusion areas, even though they're physically in contact, because why? It's a diode. As long as we keep the P grounded, we can ensure that no current will flow from the source and drain into the substrate. If it did, that's called latch up, and that would blow the chip up. That happens sometimes. But generally not. As long as if you design your chip and you put a bunch of vias down to keep that substrate grounded, you won't get latch up. It'll be okay. Because you can only go from P to N, not N to P. And so keep this at lower potential than the source or drain, and you're fine, right? But the gate, if you charge that up, now I've got a capacitor because I've got this thing is polysilicon, it's a conductor. The thing underneath is silicon, P-type silicon, conductor, but it's grounded. So this is VDD, this is ground, right? So I get this capacitive effect. And what that does, and this is the other crazy thing, I don't know how those guys figured this out. But what that does is, I mentioned the P-type silicon has holes as its majority carriers. But it turns out that it also has electrons in there too, but they're minority carriers. The minority carriers, which are actually holes in the P-type, even though I just told you that there are holes in the P-type, but there's mostly holes, but there's some electrons. They're the minority carriers. They get attracted up into the channel, and they basically connect the source and drain. You attract, so in other words, you put a 1 here, you attract the minority carriers in the channel, only in the channel, and it creates a connection between the source and drain, so it becomes an electronic switch, basically. It switches on, right? But only when you turn on the gate above 0.7 volts. And the 0.7 volts, I used to always get confused. The 0.7 volts is relative to what? The bulk, the substrate? No, actually it's not. Believe it or not, it's the gate source voltage potential difference is what the threshold is relative to on this thing, which isn't that important. But basically, 700 millivolts of here versus the source will be enough to connect those guys and turn on. Okay, so that's the NMOS. Oh, sorry, I just got done talking about that. Yeah, so this is a picture of it. So if the gate is grounded, in other words, you put a 0 in here, it just creates diodes. Diode. These guys are diodes. No connection. I mean, the source and gate are physically separated, so there's no connection there. And there's diodes here with respect to the substrate. But if you put a VDD here on the gate, it attracts those minority carriers, creates a channel, turns on the switch. A PMOS transistor is actually just the opposite. The way you create a PMOS is you create what's called a well, which is an end diffusion area inside the substrate. So I told you the substrate is P-type silicon. But if I create a localized area of N-type silicon inside there, right? And then what do I do with that? You charge that sucker up to VDD. So this whole N stuff will be VDD. That way you'll create a reverse diode here again when you put these little diffusion areas inside the well. You're saying, wait a second, you're talking about a diffusion area inside of a well, inside of a substrate. Yeah, it's like a sandwich. That's how you build these things up, like a sandwich, like that. And then that way the gate, it works the opposite way. If you ground the gate, then it creates the channel. So a P-type transistor is the same way, except to turn it on, I have to send a 0 to the gate instead of a 1. So it's the reverse, right? Okay, so that's just what I talked about. This part is a little confusing too. This is a schematic symbol for an N-type transistor, NMOS, and this is a PMOS. Notice the PMOS is a bubble here. You probably remember from 211, a bubble just means negate, just means not, right? Makes sense, right? So 0 comes in, negate it, that turns it on, right? The thing that's confusing about this is check out how they label these things. G is the gate, that's obvious, right? But drain and source, why is it drain on the top and source on the bottom here, and source on the top and drain on the bottom here? Why do they reverse those like that? What's the point of that? The reason they show it like that usually is that the drain on the PMOS, take that back. The source on the PMOS, the source, connects directly to VDD. You want to bring that up generally. And the source over here is going to connect to ground. And the drain on both connects to the output of the logic gate. Okay? Now you might say, what the why? Why is it that way? Because I mentioned that the gate voltage is relative to the source. It's VGS, right? So it's important that the drain, it's important that the source be connected to the NMOS is connected to ground and the PMOS connected to VDD. Makes sense, right? N is negative, ground, P is positive, VDD. So here's a picture. This is the schematic. So this is a schematic of an inverter gate. So what you do is you take, you create, this is called CMOS, by the way. CMOS is complementary MOS. MOS is metal oxide semiconductor. By the way, that terminology, just so you know, metal oxide semiconductor. That refers to this. But that's not metal. Modern chips don't use metal. They use polysilicon, which is something that came out after they named it. So MOS is technically a misnomer, but it just caught on. But anyway, CMOS is a way that you create the gates out of the transistors. You basically just take the PMOS and you form a pull-up network, meaning that the PMOS is responsible for setting the output to 1. When I say pull up, what's pull up mean? Pull up means you have a net, a wire, right? And you want to pull it up, meaning that you want to short it to VDD. Meaning that you want to, this guy is responsible for any input that results in a 1 output. You guys with me on that? Any input that results in a 1 output is the job of the PMOS. any input that pulls it down, pulls the output down to ground, like any input that results in the output being 0 or ground is the job of the NMOS. That's why they're complementary. They have to complement one another, right? You guys with me? Right? So what you do is, I mentioned this last lecture, is for every input you have a pair of transistors, one PMOS and one NMOS. That's why if you have a 2-input gate, there's 4 transistors. A 3-input gate would have 6 transistors. And a 1-input gate, like an inverter, would just have 2 transistors, right? Each input is connected to 2 transistors, one PMOS, one NMOS. You guys with me? Okay. Now, here's the part that's super confusing, and it seems to be needlessly confusing. When you guys took 212, you guys, not 212, sorry, 211, you guys used logic gates, but you were kind of, you kind of just used any logic gate, right? You had AND gates and OR gates, right? Well, it turns out that, see if you could follow this. Because the PMOS transistors are the ones that pull up, because they pass good ones, right? And it has to do because the threshold is relative to the source terminal. So we have to use PMOSs to pull up. And PMOSs turn on when you give them a 0. And we have to use NMOSs to pull down, and they only turn on when you give them a 1 input. That has a very important implication in that the only gates we can create with this are negated gates, NANDs and NORs. You can't do an AND gate in CMOS. It's impossible. Guys with me? I mean, you can make an AND gate, but it would require that you create a NAND gate, and then you put an inverter on the output of it. Basically, you have to build it from gates. You can't build a native AND gate in CMOS. It's not possible. Now you might say, well, geez, they lied to us because that's all we used in 211 was AND gates and OR gates. That's how all the Carnot maps and stuff worked, right? Yeah, not possible. Not possible in CMOS. You can't do AND gates and OR gates. You can do inverters. So here's how it works. If you put a 0 in here, the 0 goes to both gates, right? Now, the PMOS is going to see that 0 and say, oh, I got to turn on. So it'll pull the output Y up to VDD. Meanwhile, the NMOS will see a 0 and say, turn off. And it will disconnect from ground. Likewise, if you put a 1 in there, it'll turn on the NMOS, it'll pull down, and it'll disconnect this guy. You guys with me? Now, by the way, this has very important implications for power consumption, by the way, because as you're switching from 1 to 0, as you're turning this guy off and you're turning this guy on, and they're complementary. One will always be turning off as the other one turns on, true, but for a little bit of time, they're both on. And during which you're dumping current through this thing, which not only creates noise, which affects your noise margins, but it uses dynamic power. It burns power, which is really bad. Now you might say, well, come on, it's a fraction of a nanosecond. I mean, you're talking about, yeah, but remember, there's 21 billion of these things now on these chips. So you're multiplying that by quite a bit. I mean, depending, of course, on the switching activity of all those guys, how many of them are switching at one time. You guys with me? I'll revisit the power thing here very shortly. Any questions about that? You guys following that? So generally speaking, any gate, you can create different gates with, you have an input, it goes to, all the inputs go to 2 transistors. You have a set of PMOS and a set of NMOS, and in between you've got your output. PMOSs are connected to VDD and NMOSs are connected to ground. So how about more complicated things like a NAND gate? Well, this part's pretty neat. I was always kind of impressed by this. So to build a NAND gate, you connect. What you're doing here is you're taking advantage of the fact that these transistors are switches, And so if you have two switches, think about this a second. If you have two switches and you connect those two switches in series, then you would have to have both switches on at the same time in order to create a connection, right? Likewise, if you have two switches and you connect them in parallel, then if either one of those switches is on, you'll make a connection, right? So for example, if you take your two PMOS transistors and you connect them in parallel, meaning that their source terminals are both connected to VDD, and both their drains are connected to the output Y through this bubble, right? So they're in parallel. If either one of these are on, that Y is going to get pulled up to VDD, and you'll output a 1. Meanwhile, the two NMOS transistors are connected in series, meaning that you have to turn them both on in order to pull this Y down to ground, meaning that the source connection of this transistor is directly on VDD, and the source connector on this transistor is connected to the drain on the other connector. So the sources and drains are in series, right? That way, if I put a 1, 1 into this, if both my inputs are 1, 1, both of these guys will be turned off. Both of these guys will be turned on, in which case I'll get a 1 out, right? If I put anything other than 1, 1 in, then I'll be pulling up. This is going to create a NAND gate. Because remember, a NAND gate, if you put a 1, 1, well, think about AND. And if you put a 1, 1, you get true, right? A NAND, if you put 1, 1, 1, 1, you get false, because it's going to pull these NMOSs will pull this guy down to 0, right? So it's an AND gate, but it's the opposite of an AND gate, because it's 1, 1 gives you a 0, anything else gives you a 1. You guys with me? Okay. Now, how do you make a NOR gate? Well, obviously, it's just the opposite. You put two of these guys. You put your NMOSs in parallel. You put your PMOSs in series. That way, a NOR gate would just be the opposite. If you put a 0, 0 into a NOR gate, you'd go through those two parallel NMOSs. I'm sorry, you go through those two series NMOSs, because you have to have a 0, 0 would activate these guys, because you'd have to have two zeros. They're in series, and that would pull up, right? Just like an OR gate, a 0, 0 is the only thing that will give you a 0, right? Okay. Here's a 3-input gate. This is just 3 inputs in parallel, 3 inputs in series. So this would be a 3-input. Now the problem with 3 inputs, though, I mean, standard cell libraries usually have a 2-input and 3-input version of all your basic gates. NAND and NOR. Sometimes XOR. XNOR, I should say. But they never go beyond 3 inputs in practice. Because the problem is that if you put 4 transistors, I mean, you can do it. I've seen it done, but it's rare. If you start putting 4 of these transistors here in series, that's bad news, because each one of those transistors, even when they're turned on, has some impedance, has some resistance. And so when you go to pull that down, you're creating a voltage divider where you're getting more impedance than you want between the output and ground. So that causes issues. So what you do instead is, instead of just having, this goes back to the book's concept of discipline, where you want to limit the design choices. So you present your designer with a limited series of options for logic gates, and if the designer needs more inputs, then you just have to build multiple gates together to get there, right? Make sense? So again, you just use abstraction for that. Okay, let's see here. I just got a couple minutes left. I already talked about this, so I can make this real fast. So I mentioned that when you switch a logic gate, it temporarily shorts power and ground. That's called dynamic power consumption. This is becoming hugely important in modern chips, because it's difficult to manage the power of these really large-scale designs. The dynamic power consumption is 1/2 the capacitance times the VDD squared times F, which is the frequency that you're switching at. The capacitance refers to the total capacitance of all the transistors. Now, I mentioned that the gates on a transistor is a capacitor. So transistors, by their very nature, are capacitors. So the capacitance, and of course the wires that come out of them are also capacitors as well. So the gates and all the wires are capacitors. Remember, I mentioned the substrate of a chip is grounded. Well, those wires are running over. Are real big long wires with a lot of surface area, and they're running over top of a substrate that's grounded. So they're all the wires are capacitors too. That's what limits your clock speed, by the way. But the crazy thing is that, check this out, VDD squared. VDD squared. You have to square the VDD to get the power. That's huge. You get a huge impact by dropping the voltage, which is why we've been doing that. That's why we're getting close to inching our way closer and closer to that magic 700 millivolt threshold. And then, of course, frequency, you can try to limit transitions, and then capacitance, there's not much you can do about that. Static power consumption is the power. By the way, the CMOS, some of you might have heard of TTL logic, transistor to transistor logic. It's the actual chips that you guys used in 211. Those were TTL chips. Those were not CMOS chips. I don't know if you knew that. TTL chips are the old style transistors, chips from the 70s. Sorry, not, oh, I didn't, oh, that's weird. It's fine, I don't need it. Transistor to transistor logic just uses NMOS, and instead of the PMOSs, they just have a resistor up to VDD. And as a result, they are always drawing current. They're very power hungry, right? But CMOS, the advantage of CMOS, the reason why we use CMOS today is that it's low power. It's considered low power because the NMOSs and whenever the transistor is not switching, they're supposed to have low static power consumption, meaning that there's very low current that goes from VDD to ground in steady state when the thing's not switching, right? The problem is that as we lower that voltage down, what's happening is that the static power, even though there's very little because the effective impedance is on the order of mega ohms when that thing's not switching, that static power is becoming a larger component. And that's really frightening to people because there's nothing you can really do about static power. You can't like clock gate it. It's harder to control static power consumption. So static power consumption is power consumption that happens all the time, and dynamic is due to switching activity. It used to be dynamic was much bigger than static, but nowadays I think they're about equal. If you look at the total power consumption of a chip, they're almost equal terms. Okay, thank you. We'll meet again on Wednesday. Have a good Labor Day weekend.